Welcome to the homework help for simple machines. Now the trick to simple machines is twofold. First, you have to keep in mind that is the law of machines that it's all about, which is really the first law of thermodynamics, which means that the work you put into a machine, which is force times distance in, is going to equal the energy you get out of a machine. Force times distance out. Machines don't make energy, they just make it easier by trading force for distance. So the other thing you have to keep in mind when you're doing simple machines is to draw pictures. By drawing and labeling pictures, it helps you determine which is the input and which is the output. So let's just start with the output. I find students have an easier time with output. So here's what we find, that the output force, the force output, is the weight of the object. How heavy is the thing that's being lifted? Now the force, the output distance, so the distance output is the height that it gets lifted. So basically what we find is the output force is the weight of the object being lifted, and the output distance is the height that it got lifted. The input force is how hard did you have to push or pull the machine, and the input distance is how far did your hand or body have to move in order to achieve this force times distance. So this is you, and this is the thing that's being lifted. This is how heavy it is, and this is how high it is. With that in mind, let's try our homework. Okay, so let's try number one. Now let's see what I have. I want to push a 1,000 Newton lawnmower. Now that is its weight. So this is the output force. I want to push it into a truck bed that is 0.75 meters off the ground. So that's how high it is. So remember, high is the output distance, weight is the output force, and I'm going to be pushing it along a ramp that's 3 meters long. So this is how far my body is going to move. So that is the input distance. So let's just go ahead and try to use the, we're going to draw ourselves a picture. Let's go to the next slide. Let's do some artwork. Here's what we've got. I have a truck. There it is. I have a ramp that is going to go up into the truck. The ramp is 3 meters long. The ramp is 0.75 meters high, and I have a lawnmower. Oh golly, can I draw a lawnmower? Here it is. There's my lawnmower, and my lawnmower has a weight of 1,000 newtons. And so I'm going to use this equation here, and the trick, my friends, is to identify your inputs versus your outputs. So here you go. The weight of the object is always going to be your output force, and the height that the object is lifted is always going to be your output distance. So let's just go ahead and substitute that in. I now have 1,000 times 0.75 equals, well, I don't know what the force is going in, but I know how long the ramp is. My body is going to be moving 3 meters, so therefore I can say times, I'll just write 3 and not the 0.0. Now what that means then is force times 3 equals 750 joules, and that's meters. So now I have to divide both sides by 3 meters. And when I do that, what I'll find is the force needed to push that lawnmower is equal to 250 newtons. So I would have to come down here, and I would have to push with an input of 250 newtons in order to get this to move up here. So you notice I'm pushing with 250 in order to lift 1,000, but the trade-off is I'm going to be pushing it 3 meters in order to lift it 0.75 meters. Okay, let's look at number 2. what we've got here is a nice diagram, and what we see is this pirate, don't ask me why he's a pirate, but it's an awesome stick figure pirate, is applying this much force. That would be the input force because it's going from his hand. And his hand is going to move this distance, so that would be our input distance. Now remember, the weight of the object is always going to be the output force, and so what we want to know is how high up, how high is the rock lifted. And remember, how high it gets lifted is always the output distance. So what we're looking for is the output distance. Let's see how to do this. So in the case of our pirate, the input force was 200 newtons. And the pirate's hand was moving a distance of 1.5 meters. And what we knew was that the weight that was being lifted, the output force, was 1,200 newtons. And what we wanted to find out was how high in the air, what distance in the air was it lifted. So 200 times 1.5, that's 300 joules worth of work is being put into the machine, and therefore that's 300 joules coming out of the machine. Now, on this side of the machine, what I find is 1,200 newtons times a certain distance is going to achieve this amount of work. So I have to undo what's being done to D, which means I have to divide by 1,200. And I've noticed that students often don't like taking a smaller number and dividing it by a larger number. But my friends, that's exactly what you got to do here. And what we find in this case is the distance is 0.25 meters, which makes sense. He doesn't lift it very high. Alright, for number 3, I have a person is going to use this input force. This is how hard they're going to pull, and this is how far, 12 meters of rope they're going to pull, to use a pulley system in order to lift a goat, don't ask me why, up to a 3-meter high window. So remember, high is output distance. So the first thing we're asked to find is what is the IMA of the pulley system. Now, IMA is equal to the input distance divided by the output distance. Now remember, the output distance is always how high an object is lifted. So in this case, the goat was lifted 3 meters, and the input distance is how far your body moved, and your body moved 12 meters. And therefore, what we find is that the IMA of this system equals 4. And there's no units associated with it. It's just 4. Now, how heavy is the goat? In order to figure out how heavy the goat is, we have to use the law of machines. And let's just see if we can cut to the chase here. The input force is 280 times the input distance, how far your hand moved, was 12 meters. Now, we want to know what the weight of the goat is. The output force is the weight, and the output distance is how high it was lifted. It was lifted 3 meters, so I have to divide both sides by 3. And when I divide both sides by 3, what I find is the output force, or the weight of that goat, is 1,120 newtons. And I should round my answer to 2 significant figures, so therefore I'm just going to call that an 1,100 Newton goat. Okay, let's try number 4. What I've got here is, I want to know what the IMA of the road is. That means I need to take the input distance and divide it by the output distance. I'm not interested in the force, I'm only interested in the distance. Now, the road winds up a hill this far in order to climb into the air this far. So remember, height, which is how high it climbed, is always going to be our output distance. And how far the object moves is the input distance. So I'm going to go ahead and say, how far you move, rather, is the input distance. So what I'm going to say then is that IMA is going to equal the length of the road, which is how far the car's got to go, divided by how high. High is always going to be the output distance. And what we're going to find is the IMA in this case is 7.25806, and it looks to me like I need to round to 2 significant figures, so I'm going to say then that the IMA of this road is 7.3. And again, there's no units for IMA. Now, the next question is, number 5 says, how much force would the car's engine need to generate? Now, the car's engine is not its weight, so what I'm looking for is the input force, and I'm going to need to know all the other information. So I want to know what is the input force. I have to multiply by the input distance, which is how far the car had to move itself, 4500, equals the output force, which is always going to be the weight of the object, so 880 newtons, 8,800 newtons, times I'm going to move over, times the height, the output distance is always the height, and this is how high it climbed, so the output distance is 620 meters, and that means I have to divide both sides by 4,500. I'm sorry about my writing, people. And what we find then is the input force that the car needs to generate is 1,212 newtons. And again, I'm going to round it to two significant figures, so I'm going to say the force in this case is actually equal to 1,200 newtons. There's my answer. Well, the trick to number 6 is to keep in mind that with a pulley system, you can do this. The input distance can basically be measured from the fulcrum to wherever your hand applies the force. So let's just go ahead and draw U. Here you are. Okay, great. That's a great U. All right, so basically, from here to here is going to be, you're the input, so this is the input distance, and the output distance is from here to where the tree is. My phone is ringing. Can you hear that? So what we have is the tree weighs 3,400 newtons, and you are going to push with 860 newtons, and the distance between the fulcrum and the tree is 15 centimeters. So what we want to know, therefore, is how far away from the fulcrum is your hand. Basically, what we're looking at is this. Here's your output force, the weight of the thing you're lifting. This is going to be the output distance from the fulcrum to the output force. This is the input force, and so we're looking for the input distance. So we're just going to use that equation, the law of machines equation, and we're going to solve it for the input distance. Now if we look at number 7, we can see that, let's see, a jack is designed to move a car up 2.8 centimeters when you move your hand. So your hand is the input. So I'm going to say 92 is the input and 2.8 is the output, and I'm going to use that to find the IMA. I have my input distance and my output distance. And for, let's see, here it says how much force did you have to use. Remember, you are the input force, so I would say the input force, which I don't know, times your input distance is going to equal the output force times the output distance. Now let's see, number 9, we're going to use the, let me move this up a little bit. Didn't quite go the way I wanted, but let's just try this here. What we want to do is we're going to use the IMA equation. IMA equals the input distance over the output distance. And what we got here is, we know the IMA is 6, and we know we're lifting the piano 1.8 meters. So I know that 6 is going to be used to lift the piano in the air. That's a height, so that's the out. And I'm looking for the input. So now I have to undo what's being done to the input, and it is being divided by 1.8. So the opposite of that is to multiply both sides by 1.8, which makes this go away. So I'm going to multiply by 1.8, and what I find is I get 10.8. The input is 10.8 newtons. I'm sorry, 10.8 meters. And I'm going to round that to 2 significant figures and call it 11 meters equals the input distance. And for number 10, we have this lovely ramp here. And remember, how high something gets lifted is the output, and therefore this is the input. So generally the ramp surface is the input and the height is the output. So with that in mind, to find the IMA, I would simply say 12 meters over 2 meters gives me an IMA of 6. Now, if I wanted to calculate how hard I have to push, that's newtons. Now, U are the input, so therefore the input force times the input distance, which is how far you move, is going to equal the output force, which is the weight of the cart. Remember, weight is always our output force, times the output distance, which is always how high it gets lifted. And you know what? I'll let you do the math. Alright, so for number 12, we have this lovely diagram. Yes, I am magnificent at this, aren't I? The Michelangelo of Microsoft Paint. So, what I have here is this. I have an anvil. That's supposed to be an anvil like Coyote gets dropped on his head by the Roadrunner. And it is 45 centimeters away from the fulcrum. So I'm just going to go ahead and label this distance here 45 centimeters. And the person's hand is positioned a distance of 135 centimeters away from the same fulcrum. So even though they're on the same side, I'm going to use that rule of this is my output distance because the weight is this far. My hand is the input, so this right here is the input distance. So to find the IMA, I'm going to say 135 divided by 45. I'll let you do the math. Now, how hard will the person have to lift? That is, I'm looking for force. So I want to know how much muscle power, how many newtons of force this person has to input into the machine. Alright, so therefore I don't know what the input force is, but I do know what the input distance is. It is this here. That doesn't mean his hand has to move 135. With a lever, I can just take the distance between where your hand applies the force and the fulcrum, which in this case is 135, and I can call that the input distance. And the output force is the weight of the object always. So the weight in this case is, it's right here, it's 4840. So 4840 newtons times, in this case, the output distance is the 45 meters between here and here. So I'm going to say 45 centimeters, and I'll let you do the math. And our last one, we have a catapult, which I always like. So we know is that the output weight, the object being thrown, is this distance away from the fulcrum. So therefore, you know, I want to draw this. Okay, so we have is a boulder that's in a catapult. There's my catapult. Alright, and what I find is that this distance here is my output distance, and the input force, which is actually going to be an object here, let's say, the input force is positioned only 2.2 away. So this kind of catapults are kind of strange. They're not designed to make it easier to lift it. They just are designed to make this move faster. And I know, let's see, that the counterweight weighs this much. Now, it's kind of weird. The counterweight is what's doing the work on it. So this is actually going to be my input force, and this is going to be my input distance. And so the question is, how much force is going to be exerted on the projectile? So what we're going to do is we're going to say the input force, let's see, yes, the input force is 9,800 newtons times the input distance, which is going to be this distance here, which is 2.2 meters, is going to equal the output force acting on it, which we don't know what it is, times the output distance, which is going to be from the fulcrum to where this is having its force applied, which in this case is going to be 4.8 meters. And again, I will let you do the math.